Our brain is the source of both intellectual capacities and emotional behaviors. It's what makes us human beings. Understanding the functioning of the human brain is one of the greatest scientific and philosophical challenges of our time, as well as one of the ultimate frontiers of modern human biology and cognitive sciences. Brain research currently represents a multidisciplinary challenge, since it involves several research approaches from genetics, cell biology, physiology, imaging, bioinformatics, anatomy, and clinical investigations to behavioral sciences. During the last decades, brain research has made great progress on all fronts, but much more is still to be discovered. In fact, despite eminent and numerous attempts to understand complex thinking, insight problem solving and language acquisition, one is left with the feeling that an essential component of these processes is being overlooked.
And so the problems have to do a lot with whether we have a kind of pattern-based intelligence, which is you recognize a pattern and then you have a solution associated with the pattern which you then use.
The remarkable and deep similarities between thought and evolution enticed researchers to propose a hypothesis called the Neuronal Replicator Hypothesis, NRH, that states that a Darwinian process of production of cognitive adaptations by natural selection can run in real time in the neuronal network of the human brain during its lifetime.
But if you look at neurodarwinism as it was conceived, it's quite clear that what happens in that system is something like selection on a standing variation and not bona fide evolution where you would produce newer and newer variants through many generations on which you could select to get to cumulative adaptations.
It might be happening to you now. While you're watching this video, your brain is working and learning changes. In your brain, neural networks are activated and reformed, and possibly some candidate solutions are replicated and tested unconsciously, allowing you to come up with creative adaptations in your daily and professional life. It has become increasingly clear that genetic evolution is a process of insightful search, because it's able to learn from past environments to structure and improve future search operators.
And this kind of thinking further is called insight problem solving. And so this way you can solve problems which are not routine and which require a kind of creative step.
Insight is a process of creating new and more useful representations of a problem that in many cases enhances the understanding of cause and effect and guides future search.
And that's really what the Insight project is all about. So it's really about pushing the limits of current artificial intelligence techniques and methods to go in the direction of human intelligence, which means to go from, let's say, animal-like intelligence, or as I said, the idiot-savant, kind of intelligence, towards deeper, more reliable, more robust, and I would say, more satisfactory kind of intelligent behavior.
Open-ended human problem solving and open-ended learning remain far superior to what can currently be achieved by machines, despite considerable progress in modeling and implementing routine problem solving.
For example, in machine translation, if you recognize the sentence as a pattern before, and you have in your database, you have the text, let's say you translate from English to French. So you see a pattern in English and you see the pattern in French and you link it up. then it will work. But if you have to go further, like if you have to use the grammar or you have to use the meaning, then it is no longer possible to just do this pattern-based recognition. And particularly for robotics, of course, in robotics, you can manipulate things or you can solve problems because you have seen in the past a solution. You recognize here is the same problem, and so we replay it, we do it. That's possible. But often a robot might get stuck, or there's something else in the environment which you had never seen before, and then you require a deeper understanding. And this is what we humans can do.
Insight researchers prove that the neural replicator hypothesis is the plausible missing ingredient that can unfold human brain dynamics.
And this idea, which we call Darwinian neurodynamics, is intended to correct an error in Gerald Edelman's theory, which he's called neural Darwinism, which is actually not Darwinism at all. So we're basically trying to explore whether there are replicators in your brain.
Previous related approaches have been either sketchy, metaphorical, merely philosophical, or have used selection but not replication. Insight has been based on and has refined plausible neurobiological foundations of neuronal replicators, despite the fact that neurons do not reproduce.
We have now a model that might bridge the gap between the behavioral level and the neuronal level, where we can pinpoint the cognitive processes that are responsible that new rules were established in the system, how to overcome impasses, and to find new strategies and ways to solve difficult problems.
The NRH has been investigated in 3 ways. First of all, the hypothesis has been worked out using formal models and computer simulations. Its empirical relevance has been tested both from the viewpoint of neurophysiology, using cell cultures, and from the viewpoint of human psychology, using neuroimaging and psychological experiments. Finally, its ICT application potential has been tested for 2 critical domains: robotics and language communication.
Another thing we find out is that during insight problem solving we have several insights. The first insight I would call is to realize that there is something wrong with my initial approach. The second insight is when I get stuck in an impasse, that I realize how to overcome this impasse and what can I do to overcome this impasse.
Robotics work is aimed at testing whether Darwinian neurodynamic controllers can be constructed that allow robots to engage in open-ended creative autonomous exploration.
We can make robots that exhibit creative behavior, artificial curiosity, and artificial creativity by evolving ideas in their heads about what to do.
Language processing research focuses on testing whether detailed models of language learning that are based on a replicator dynamics of grammatical constructions is effective for explaining and synthesizing creative linguistic performance.
The main thing I've been working on so far is developing a system for robots, such as the one you see here, where we can quickly fabricate a wide diversity of different robot morphologies so that we can test out different algorithmic ideas coming from the other project partners and that we've also developed ourselves.
After 4 years, the results obtained by both experimental and theoretical works of the InSight Consortium point towards the possibility that Darwinian dynamics are at play at various levels in the nervous system.
And we have some basic algorithmic results of learning on these robots to do various tests so that they can quickly evolve, for example, a control strategy for locomotion and coordinating their limbs.
Today, the InSight project has achieved a better understanding of exactly how we solve problems by examining how ideas in our brains could evolve throughout our lives.
Our next steps in the project are we try to find a neural implementation of these findings, and we hope that we can bridge the gap between the behavioral level, because most of our experiments operate on the behavioral level, down to the neuronal level, and so we can shed light on these underlying processes that might be important for creativity out of the box.
In the future, it is fundamental to further explore the role of Darwinian dynamics in robots, to extend the work on copying information in biological neural networks, and to further develop the discovered models of ensemble learning in spiking networks, incorporating further Darwinian elements. Overall, the implications of the InSight research are far-reaching. One interesting twist might be that the evolutionary processes going on in the brain could even be more powerful than in the wild, as they're modified and guided by learning. While much of this remains speculative and further refinement of models required, the InSight project has begun to put flesh on the bones of a theory that could one day lead to self-learning machines, smarter language translation, and transform teaching and problem solving.